Okay, let's see, checking. Yeah, okay, we're going. So, all right, last time we were talking about the implicit function theorem. Again, you probably saw kind of a version of this in a single variable calculus class. Probably wasn't treated thoroughly because they didn't have the tools to do so at the time. So, reminder, what we're talking about can be said in different ways. If you have an equation, can you solve for one of the variables as a function of the other? Let me say that differently. Suppose you have a level set. Can you view that as being a graph? Let me say that differently. If y starts off as an input variable, can you view it as being an output variable? Right? There's different ways to think about what we're talking about here. I emphasize that we're only considering the question locally, right? So if I look at a given point on the curve in question, right? We don't really care about stuff that's happening, let's see here, wrong color. Let's see here, let me do it like this. We don't care about stuff that's happening way up here, right? This is not a failure of the vertical line test as pertains to the question that we're asking. We're only asking about locally. We're only interested in what's happening just on that little bit of curve right there. Phooey on everything else, right? Okay, so at this point, locally, no problem. At this point here, locally, no problem. But at this point, there's a problem. As we discussed last time, no matter how little, let's see here, let me try to do a better job with the drawing. No matter how little of the curve you restrict your attention to, however little it is, right, there is going to be a failure of the vertical line test. I mean, there's nothing you can do, right? There's no way that you can view this locally. This little blue curve, however small it is not a graph of y as a function of x. It can't be. There's no way to do it. Okay, so that's what we're interested in. And we talked, moved me to the wrong spot. We talked last time about why we care about this, and that is, just as a reminder, sometimes, and this is what you saw back in single variable calculus, sometimes when you are looking at an equation, you want to be able to talk about dy dx. Right? I mean, implicit differentiation and all that. Okay, well, can you write down dy dx? Well, you can't write down something that you don't even know if it makes any sense or not. It's not a question about whether there will be an answer ultimately. The point is we don't even know if it makes sense before we get to the end of the calculation. That's not mathematical reasoning. You can't do that. Right? So, the only way you can know if dy dx makes sense is if you know that y is actually a function at all. We take derivatives of functions. That's what a derivative does, right? There is no such thing as a derivative of a bicycle. That's crazy talk, right? So y had better be established as, at least locally, a function of the other variable before you go around taking derivatives of it. Okay, so we talked last time also about the big picture of how to make this decision, right? How would we decide if you can or can't do this? And I argued that by showing you a picture of what a problem looks like. Loosely speaking, I like to think of this as the curve wrapping under itself, and in particular, it's at the specific point on the curve where that wrapping under itself happens, right? There is that exact one point. That, of course, would mean that there is a vertical tangent line, which, of course, would mean that there is a horizontal gradient of f, because, after all, gradients are always perpendicular level sets, established last time. And if you have an equation where f is a constant, that is a level set, so the gradient of f has to point perpendicular to that. And, of course, we talked last time about how a horizontal gradient would mean that the y partial is 0. Okay, is this all ringing bells? Sound familiar? Everybody good? All right. Okay, so that gives us this initial conclusion, which isn't exactly the helpful observation we need. If you have a problem then that y partial will be 0. This statement, as stated, presumes you know the answer to the question you're interested in, and then tells you something you're not clear what you care about. So this, as phrased, is not that useful. But if we look at the contrapositive, we get to something that actually is useful. Let me scroll up so we can see better. Here is an algebraic test that's easy to perform. Partial derivative, super easy to compute. Checking to see if something's 0 or not, usually pretty easy, right? Arithmetic at most. And the conclusion is an answer to our question. So this is the form that we're actually going to be using the implicit function theorem. So technically, every old single variable calculus example where they did implicit differentiation, right, you think about it, implicit differentiation starts you with an equation, and then you just start going around taking derivatives and writing down dy dx and just going crazy with the calculations as if that's legal, as if that makes sense. And technically it really didn't at the time, right? That was pretty careless at the time. Now we know how to establish whether that was or wasn't garbage nonsense, right? If you take the partial derivative with respect to y, confirm it's not 0, then we know, no problem, y is a function of x. Go ahead and do all the implicit differentiating you want. All right, so that cleans up the single variable version of this. Now let's go on to our actual goal here, which is to do the multivariable version. You're going to notice this comes at you in a similar way. Now I'm going to suppose that I have an equation involving 3 variables. That's going to give me a surface, not a curve. Surface in space, no less. And I can ask the analogous question. If, in fact, I have a level set of some function, can I view one of the variables, let's say z, as being a function of the other 2? Again, not obvious, right? Z comes to us as an input variable. We would like to assert that we can view it as an output variable. Not clear. And again, that's local, so we're only looking sort of nearby. And so, if I have a point, and let me zoom in a little bit. If I have a point like, right there on the surface, I'm not concerned about the fact that technically this, there's a vertical line test problem, because I'm only interested in what's happening locally. And locally, looking only nearby that point, there's really only a little bit of surface right around that point, right? And looking only at that little bit of surface, now I ask, there we go. I ask rhetorically, does this pass the vertical line test? And yes, it does, locally. Right, so for a point like this, the answer is yeah, sure, go ahead, view z as a function of x and y. It's all good, cool, no problem. But you can see that there are points where this is going to fail. And in particular at a point like that, where the surface is in the process, at that right there, you know what I'm talking about. Let me not say keywords I'm not allowed to say. But at that point right there, the surface is in the process of wrapping under itself. It's just, however little of the surface I look at, art challenge. Now let's see if I can represent that kind of. Right, that little bit of surface, however little there is, it's going to fail the vertical line test. Right, just a 3-dimensional version of what we saw with the curve just a few minutes ago. All right, so how do we identify in advance whether we're talking about a point where everything's good or a point where we have a legitimate problem? The argument is very, very analogous. If I have a problem and the surface is, in fact, at that very point in the process of wrapping under itself, then I will have a vertical tangent plane. Now that's a geometric appeal, right? The process of wrapping under, you have to be vertical where you're wrapping under. Geometric appeal. Oh, wait a second. Vertical tangent plane means that I'm going to have a horizontal gradient. Because again, gradients are always perpendicular to level sets. And very, very importantly, our assumption is that the surface comes to us as a level set of a function capital F. So the gradient of capital F will be perpendicular. And then again, you can write down what horizontal gradient means. And in fact, all it means is that third coordinate of the gradient must be 0. And of course, that third coordinate is the z partial. Okay. All right, so now what I want to point out before I finalize and state the general theorem, which again, I'm not going to be rigorous about it. I wanted you to have a sense and an intuition for kind of morally what's going on here, but the rigor is not what this course is about. Let me just point out that just like in the single variable version, here we go, whichever variable you want to view locally as a function, that's the variable whose partial has to be non-zero. That was the one way to phrase this in the single variable version. By the way, for practice purposes or entertainment purposes or whatever, think about how this picture would be different, how this analysis would be different if you wanted to consider viewing x as a function of y. Right? Things would change. What would remain is that the variable you want to view as a function is a variable whose partial you have to look at. Okay. Notice now in the three-dimensional version of this, we were trying to find z as a function of the other variables. And notice the variable that we want to view as a function, again, that's the variable that you look at the partial with respect to. Right. Okay. All right. So that's the pattern, and that's what gives us that's what allows us to suspect this theorem right here. If you have, and again, all the formalities we're putting back into here, you do need the function to be continuously differentiable. That's bad things happen if that's not the case. Don't worry about that. But if you have an equation involving n variables, notice n variables, and if you want to view one of the variables locally as a function of the others, look at the partial with respect to that variable. Make sure it's not 0, and if that partial is not 0, you're all good, no problem, everything's fine. Go ahead and take all the partials you want to, it's all fine. Okay. All right. And I've already emphasized this boxed point. But whichever variable that you want to view as a function, that's the variable that you take the partial with respect to. All right, let's see an example of this in action then. Here is a surface, and I want to state for the record just before we get into it that I have no earthly clue what this surface looks like. Right? I don't see any foot in the door. It's got cubics and multiple mixed terms and yikes. No idea. You can't just say, I'll just draw a picture and use my geometric intuition. No, you won't. Right? Forget about it. No idea what this thing looks like. But I can still reasonably ask the question, can I view x as being a function of y and z? Maybe for whatever reason, this equation here describes a constraint that I'm dealing with. X, y, and z are parameters that are important to me for whatever reason, and I need to know if I hold y constant and change z, I want to know how much x changes. In other words, I kind of want to take the partial of x with respect to one of these. In other words, I need to view x as being a function. Can I? Is that cool? or do we have a problem? Right? So I'm going to use the theorem on the previous page. The variable that I want to view as a function, that's the variable that I take the partial with respect to. Now, reminder, what do I take the partial of? I take the partial of whatever function it is of which I'm looking at a level set. Again, really important to the argument, right? You have to be looking at a level set of a function specifically. So if the equation comes to you with terms on both sides, you got to toss everything over to one side, nothing but constant on the right. Zero's kind of convenient, but it doesn't matter. If you wanted to put this 27 over here, okay, that's fine. As long as it's a constant on the right-hand side. I don't know. I'm just kind of, I'm a creature of habit. I like to have everything on the left and 0 on the right. Nice and simple. Doesn't matter though. Okay, so this is the partial derivative we look at. It's easy to compute. I can plug in, let me clean up my mess here. I can plug in the point we're interested in. We're interested in what's happening near this point 1, 2, 3 on our surface. So I'm going to plug that in. And it's not 0. So we're all good. So sure, you want to treat x as being a function of y and z? Go ahead. Safe, risk-free, no problem. Everybody on board? Okay. All right. Now, here's where things start to get a little scary looking. So I like to flash this first if I really wanted to be careful about how I treat this next question. This is arguably the diagram that I should be drawing, and I have an alternative that we're going to do instead. So don't worry too much. But in general, now back to our general version. Suppose I have some equation viewed as a level set. Suppose that I've done what we already said we were going to do. I've taken the partial with respect to xi. I've confirmed that it's not 0. I conclude that xi is a function. Right? So now with all of that established, with xi being a function, how would I take a partial derivative of it with respect to, one of the variables that it's a function of, right? So xi is a function now. It's a function of all the other variables, and I want to take a partial derivative with respect to xj, and this is where the diagram starts to get a little weird and confusing, because here's xj, but I can't take a partial. Those are in the same column. This gets weird, right? So here's the little math crime that I'm going to commit. I'm about to break my own rule. Don't try this at home. But notice this diagram that I have here is set up to actually be a composition of actual functions, and thus this is something to which I can apply the chain rule. Right? Our chain rule is strictly and only for compositions of functions. The problem is I haven't explained what those x1 prime, x2 prime are, and it's a lot to keep track of. So here's the question.
So you took the partial derivative, and xi is a function of the two other variables in this respect.
Uh-huh.
But then on the second line below that, you're saying that but xj or x sub j is not a function of the other variables. That's what you're saying there. When you say f equals c and the partial of f with respect to x sub j.
So you're going into stuff that I don't want to do. The whole point to this is that I don't want to talk about this. Yeah. No, because it is confusing, right? So what I wanted to do is point out that this scary business here is a more proper, careful treatment. But here's what we're actually going to do, and this is just going to be easier to play with. So now, I want to make, before I start going into the details here, I want to confess, this diagram does not follow my pretty crisply stated rules, right? Back when we were talking about the chain rule, you can't just draw any diagram you want. You have to have a composition of functions. This violates that rule. But again, in a don't try this at home sense, I promise that in this particular case, this is okay. It doesn't follow the rules. The rules are excessively safe. It's going to be fine if we just think off of this diagram, and I'm just going to ask you to trust me on that. So here's the argument we're going to make. We have that f is a function of all of these variables, as a result of which I can view xi as a function of all of the others. Again, I know that looks weird. I get it. If you're not, it's fine. And I ask the question then, if I start changing xj, what's going to happen? How do changes propagate? If I wiggle xj, what happens? Well, I mean, there's two things that happen. I mean, again, this is a partial derivative, so all these variables are constant. None of those change. But xi is a function of xj, so xi is going to change. And wait a minute, as xi changes, that means f is going to change. That gives you this term that comes from that green path. But here's another thing that's going to happen. If you change xj, xj itself is immediately one of the input variables for f. So that is a direct path along which changes in xj can propagate to changes in f, and that gives you this term. So keeping in mind that altogether f is a constant, right? The whole point to this thing is that we started looking at a level set of f. In other words, f is constant. Grand total, f can't actually change. F is not allowed to change, so the total derivative of f is 0. And with all of this in mind, notice that the thing we were interested in happens to show up, right? The whole idea is I wanted to know how does xi change per change in xj. Viewing xi as a function, what's its partial with respect to xj? And I can just straight up solve for it. And you get this right here. Nice, compact, handy-dandy little formula. Everybody all right? Now there's a landmine, something to watch out for. It's very dangerous. Oh, man, this is a big one. Please be super careful about this. A lot of students will figure, hey, check it out. Those cancel, right? You see the temptation? And then, hey, wait a minute. Also, the xi, partial xi down here, that's in the denominator of my denominator, which means it kind of goes up into the numerator. And then let's see, the partial xj is in the denominator of the numerator. That's in the denominator. And a lot of students will then say, hey, I don't need this minus sign. It kind of looks like, I mean, again, in a sloppy, careless cancellation of factors sense, it looks like you don't need the minus sign. And this is way wrong. This naively assumes that that partial f and that partial f are the same. They are not. Right? It assumes that this partial xi and that partial xi are the same. They're not. This is one of the tragedies of this kind of fraction notation to represent partial derivatives. It makes it look like it's a fraction. It's not a fraction. Partial xi by itself is not a thing. Right? So I went on at length about this when we were doing the chain rule, right? That you just can't do this. This is fundamentally wrong. Again, this is very tempting, though. So here's why this minus sign here is so important. This minus sign is the only thing that separates a perfectly valid equation, perfectly valid tool to use, full credit, from, if you miss it, not only a wrong formula, but a formula that betrays a fundamental misunderstanding of everything involved. This represents a fundamental misunderstanding of the chain rule, a fundamental misunderstanding of how of what partial derivatives even are. Right? Now, again, it's not about answers, it's about ideas. Right? And so, again, it's tempting to say, oh, it's just a sign error. Ooh, no. This is not a... Look, we've all... I know I have. I have on many occasions had -1 cubed and somehow came up with +1 from that. You know, we all do little goofball, that's a triviality that every human's going to make mistakes on that kind of thing. So all that betrays, if you make a oopsie with the sign, right, that just, okay, yeah, sure, human micro-fallibility. It's not a big deal. That's not what this minus sign is. Right, this, not putting that in here makes you indistinguishable from someone who really, really, truly has no idea what's going on. Probably, I don't know, let me not overstate it, but this is one of the most important minus signs in the course. So please be very careful about this. This will be a big deal. That minus sign there will amount to just a lot of points. Okay. So please keep that in mind. Now, what I will point out about this, and this is kind of a little silver lining situation, other than this minus sign, I mean this garbage nonsense about canceling, that, let's see here, where's a good color, that, this cancels with this, and that, that goes there, and the blah, blah, all the nonsensical treatment of these as if they're fractions. It's actually pretty handy for keeping track of which variable goes where. Now, I use it for that purpose, right? And it's garbage. But it's really convenient garbage, right? So I'm all in favor of that, right? Just make sure that you don't forget the minus sign. Again, cannot emphasize that enough. Okay, all right, enough of that. So moving along. You'll recognize this equation. This is the exact same equation we looked at recently on the previous page. There we go. We have already established in this equation that x can indeed be viewed locally as a function of x and y. We did that on the previous page. So we don't have to do it again. We're good on that point. So with the understanding that x is indeed a function, I can ask this question. Given that x is a function, I can talk about its partials. Perfectly reasonable. Yeah? Everybody happy? Given that it's a function, and given that it's okay to ask about its partials, how would I actually compute that partial? And I'm just going to use the formula, basically the formula from the previous page. It's not exactly the same because the variable names are different, but you'll notice where I'm getting this formula from. I'm using my little garbage little hack. Step 1, put that minus sign in there. By the way, I think it's good strategic policy. I encourage everybody to do this. Write the minus sign first. Can't forget it if you've already done it, right? So I put that minus sign in there. Okay, all right, now I'm safe from that severe blunder. And I go ahead and put that there because that's that's the function I'm taking the partials of. That's the function whose level set I'm looking at. And then just play the usual reasonable games. The denominator variable comes from the denominator of the numerator, and the numerator variable becomes from the denominator of the denominator, again, exactly as you would kind of naively suspect from this nonsensical cancellation argument. Okay? And notice that gives you the formula. I think this is a really easy way to remember it. That's certainly how I do it. I'm all for you doing it that way. Cannot emphasize enough. Again, don't forget the minus sign. And with that done, just got to compute a couple of partials. This function right here, right, the z partial is that. Same function, the x partial is this. right? Again, just like on the previous page, we're interested in at this point 1, 2, 3. So I'm going to plug that 1, 2, 3 into this expression. Arithmetic, yada, yada, yada. And our answer is, anyway, here, right there. Is everybody all right? Okay. All right, now, last point, and then we're going to move on to, finally, Chapter 3. So, these two examples that I did are really two parts of the same example. I started with an equation. I ended with a computation of one of the relevant partial derivatives of one variable with respect to the other, but notice that there really were two steps in the process, right? I had to first, step one before you do anything else, I had to establish that x is locally a function of y and z. I hadn't done that, I can't even ask the question of what is partial of x with respect to z, because you can't take a partial of something unless you know it's a function, right? So step one, establish that it's a function. And then step two, once you know that it's a function, then how do you compute the partial derivative? And, we have this handy formula. Don't forget the minus sign. And plug and chug. Okay, so the thing I want to emphasize, questions won't necessarily come to you telling you every step in the process that you're supposed to do. That's part of understanding the background of the material, is to realize what has to get done, right? So very often, this is just how life comes at you, and therefore, on my exams, this is how my exam questions are going to come at you. It's not going to say, hey, don't forget to check that this is actually a function, right? You have to remember that. Remembering to do that is part of proficiency with these ideas, right? So don't just assume that the thing you've been asked to compute a partial of is actually known to be a function. You've got to remember to confirm that. Okay. By the way, just for your curiosity, to me, when I grade these questions, I count typically, I think this is pretty reasonable, I count this part, establishing that x is indeed a function before I start taking derivatives of it, is about half of the points of the question. And then the plugging into the arithmetic and actually, into the formula and doing the resulting algebra and arithmetic is about the other half of the points. So don't just skip part A, right? That'll cost you half the points. Again, big deal. Is that okay? Yeah.
Yeah. So just to confirm, so
yeah.
It's like obviously looking at the formula. If you were to not check A, you would end up dividing by 0.
Yes.
Like you'd reach that contradiction.
That's true.
So it's like there's no retroactively like.
I'm not prepared to say that you can't get a wrong answer, right? You're quite right that the thing that you need to not be 0 is also something that you need to not be 0 in order to be able to write down that fraction. But there's just no getting around the fact that if you write this down without having established that x is a function, then you ventured into garbage. And you just can't do that in math, right? So it's not about, again, you got to keep in mind, it's not about the answer, it's about the reasoning. So you're guilty of bad reasoning right here already. And whether or not you would safely arrive at the right answer is just not what this class is about. Does that make sense? Yeah, and I totally get the temptation. But that's something we got to be really careful with. Yeah. Okay. Yeah.
So in the case that you would wind up with something where it's just not defined there, like you can't write it locally as a function of the other variables, you would just say like dx dt does not exist or can't find.
That's right. You would just say, if you took the partial of f with respect to x, and x turns out that it's not locally a function, then you would just say this question's garbage, nonsense. I can't take a partial of something that's not known to be a function. ask a better question. Now that said, I think that would also be, just, from a test design standpoint, that would be I would have to be very careful about how I phrased that, because I don't want to create a situation where I actually directly mislead the student. I think that wouldn't be fair, right? But again, that's not mathematical reasoning, that's strategic reasoning. You still have to check, but outside of Math219, right, where you have no such promises, you would just say, you can't take this partial, it's not a thing. You're trying to take a partial of something that may or may not be a function. Yeah. Right. Okay, so that's it for Chapter 2, and we move on now to Chapter 3. And let's see here, back to here we go. So we've already talked about 3.1. Remember, I did 3.1 before the chain rule because I find that to be a useful tool. We're going to entertain the idea of the length of a parametric curve here. This is just a kind of a quickie little digression. I expect to get through all of 3.2 today. It's just a couple of pages of notes. And so here we go. If I have some parametric curve, right, x is a function, position is a function of time, then I can talk about a piece of that parametric curve and how long is that little piece of the parametric curve. All right, so the first tool that we're going to talk about here is this thing called the dx vector. Let's see, let me do this in purple. The dx vector. We've written this down before. dx is a differential. This represents a displacement, right? If I'm at a certain point and I'm moving along, this represents how much I change my position, right? X means position, d means differential of, and so this represents a differential position or some small little displacement in my position. Okay, so the idea then, if you in fact are moving along a curve, and if you have position as a function of time, I think it's a pretty easy pitch that dx is x prime dt. Velocity times time gives you displacement. Arguably kind of a fundamental, dare I say, that's the definition of velocity, right? But it's a pretty basic idea, right? Velocity times time gives you displacement. Is everybody okay with that part? Yeah. Okay. Which means, in fact, of course, also you can write x prime as v. Okay. All right. Now here's a related thing, and that is, how long is the piece of curve? Now, these are not exactly the same thing, right? And if you think about it, the little piece of curve right there, well, it's right there in the name. It curves, right? The arrow representing the dx vector is intrinsically straight, right? But you can see that the dx vector kind of tracks that little piece of curve, and if at some given moment I'm here, and then some differential amount of time later I'm here, okay, well, yeah, the curve did eventually curve, but at this instant I wouldn't know anything about that, and my linear estimate of the length of that little piece of curve would just be based on what's happening at this point. And at this point, I'm going with a certain velocity, and if I want to know how far I'm going to have traveled after a certain amount of time, I would just say speed times time, right? So the big idea then is that our linear estimate of distance is that it should just be the magnitude of the dx vector. It's not going to be the exact distance, but it will be the differential, because differentials are linear estimates. Is that cool? Okay. And, of course, from above, that means that it's magnitude of v times dt. Okay. All right. Now, related idea. this thing called the unit tangent vector. So that is a pretty handy thing. We're going to be using capital T here a lot. By the way, I've seen this in multiple books. I wouldn't go so far as say it's a standard, but it's a common choice for the unit tangent vector. It is a unit vector, meaning that it represents a direction, and being tangent, well, it's pointing in the direction that the curve is going. So this is our tool for representing the direction of the parametric curve. And not hard to see what that would be. If I know the velocity of the parametric curve, velocity is, of course, not necessarily a unit vector. Velocity is arbitrary. The magnitude is the speed. Who knows how fast we're going along this curve? But the unit vector pointing in that direction, pretty easily related to it. You're just going to divide the velocity by its own magnitude. That gives you the unit vector pointing in that direction. That is my unit tangent vector. Yeah? Very good? Okay. All right. This gives rise to another useful observation about the dx vector, an alternative formula for the dx vector. I claim is T ds. And the way I'm going to show, there's a couple different ways you can think about this. I mean, one way to do this is to just think about, all right, well, this is a direction times a magnitude. T is a unit vector. ds, therefore, is the magnitude of this product. So this product is a vector that, by virtue of the T, is pointing in the direction that the curve is going. And by virtue of this second factor, the magnitude is ds. Okay. What do I know about the dx vector? Well, it's pointing in the direction that the curve is going. And as previously discussed, its magnitude is ds. So I can just, from that point of view, I can instantly say dx is the same vector as tds. These have the same direction. They have the same magnitude. It looks like a duck. It acts like a duck. It's a duck. Right? Does that make sense? All right. If you like algebra better, then notice that we have a formula for t right there. And we have this formula for ds right there. And notice that magnitude of the velocity cancels, and you're left with literally exactly just this, which we've already seen is dx. So take your pick, a couple of nice points of view there. And with that established, and by the way, this picture and these equations, this is going to come up a lot, especially when we get into chapters 6 and 7. It's going to be all over the place. So arguably this is really the most important part of 3.2 right here, is understanding these various objects that relate to a piece of parametric curve and how they relate to each other. So please be very careful about this stuff here. It's a big deal. It's going to be a big deal. Okay, so but now let's get back to computing arc length. If I have a little piece of curve such as that right there, and I want to know the grand total length, the total length is, I argue, the sum of the lengths of the individual little pieces there. We know how to compute the lengths of the individual pieces, right? The lengths of the individual pieces are v dt. And thus, nice handy little formula for how to compute the arc length. This overall arc length is just that integral. And again, I think it's a pretty easy pitch that total length is an integral of speed dt. So you get in your car and start driving down the road. You want to know how many miles you drove? Well, yeah, speed times time and add it up over your whole trip. It's pretty believable, I think. Okay. All right, so computationally, this is very straightforward. If you have a position parametrized, right? And you want to know what's the length of that curve. Well, between 0 and 1, we're just going to be adding up all of our little ds's. Our ds's are, of course, going to be speed times dt. Speed is the magnitude of the velocity. The velocity is the derivative of position. And sadly, the algebra gets pretty unappetizing there, right? This is not a convenient integral. But this is the integral that would represent the answer to the question. And so that's one of the reasons I don't really like spending a lot of time on this stuff, is because it's impractical in most cases. If you do find yourself in a real-world scenario, of course, you can toss this into a computer, or you can do a numerical estimate, Simpson's rule, or what have you. Okay. All right. So the next thing is, this is an interesting idea, the idea of parametrizing by arc length. Again, this is not something we're going to be able to spend a lot of time with. I'm going to start by pointing out that curves have lots of parameterizations, right? So now everybody knows the graph parameterization. But here's another alternative parameterization. Notice that this formula for y is the square of this formula for x. So this also satisfies that equation. This is also tracing out the same curve. Right? And you can think of this as coming from a substitution, namely, I just took this formula for t as a function of q, plugged it in, and that's what resulted. So this is one way to view a reparameterization, and that's exactly what we're going to do over here. I'm going to create a second parameter. X comes parameterized in terms of t. I'm now going to call distance my new parameter. I do have to set a starting point. This is my t equals 0. That's what I'm going to call sort of the base point for the curve. But then, I can consider position as a function of how far have I traveled along the curve. And I point out that y'all have actually seen this before, maybe not in a math class, but on a road trip. Mile markers, right? As you go along the road, you're driving along the highway. I don't know if you've noticed these. I don't know why I've noticed them, but every mile there's a number in there. It says, 163. Then a mile later, 164. Each one of those has a location, and it is indicated that location is determined by how far you are down the road from either probably the I-95 or the state courthouse or something. I don't know, some arbitrarily designated point. Right? So this is really just that same idea. Now S is easy to compute. We already wrote this down on the previous page. So if I have gotten to a certain location at a certain point in time, I just have to integrate per the formula on the previous page up to that moment in time. Right? And there's my arc length. This formula weirds out a lot of students. A lot of students are like, wait a minute, what's with this funny looking little Greek symbol? Is that a T? It doesn't look like it. I'm scared this might not be a T. Oh my gosh, is that Greek? Right? Yeah, it is. It's the Greek letter tau. It's no big deal. It's nothing to worry about. I just can't use T here. T, I've already decided, represents my endpoint of my interval. T then has to be a constant for the purposes of this integral. It can't also be the dummy variable. So tau is just an alternative dummy variable. I didn't really do anything there. The dummy variable that you choose didn't mean anything in the first place. So it doesn't matter if you change it. Okay. All right. So with this noted, you can solve for t as a function of s. Plug that in here. The result is position as a function of s. mile marker location as a function of how many miles you are down the road. This is what we call an arc length parameterization. It's nice in certain ways. It is intrinsic to the curve. Where the mile markers are on the highway does not depend on the traffic speed. It shouldn't depend on the traffic speed. It's got nothing to do with the traffic, right? It's intrinsic to the curve itself. It's part of the road, not the road trip. Right? It's also kind of nice to observe that the arc length parameterization has unit speed, because if you just write down the single variable chain rule for the parameterization and take the magnitude of both sides, notice that this is the magnitude of the velocity, which is the speed, and this is the magnitude of the velocity, which is the speed. So those are literally the same, and thus the arc length parameterized speed is 1. So nice little thing. There's an example here. The purpose of this example is to point out what a pain these calculations are. So from a computational standpoint, these are always kind of stinkers. But this is an example of how it plays out. Okay, see y'all later. Have a great weekend. See you on Monday.